Hi everybody, I hope you're doing well. This lecture is on section 14.7, extreme values and saddle points. If you'll recall in Calc 1, we used the first derivative to find local extrema. In other words, local minimum and local maximums. Here's a local max. Here's a local min. Please recall that we set the first derivative equal to 0 to find those, because that gave us the slope of a horizontal line, which is 0. Again, slope of a horizontal line is 0. The slope of a tangent line to a curve is one of our definitions of a derivative. Also in Calc 1, we had absolute mins and absolute maxes. Those are absolute extrema. For example, on this graph, the point right here is an absolute min. The point right here, that value, the y value, would be the absolute max. The way that we found the local min and local max in Calc 1 was to take any first order critical points that we have, such as in this instance 3 and 5, and make a first derivative number line. We put those values on the number line, the critical points. We broke the number line down into regions, and then we tested numbers such as 2, 4, 6 into my first derivative's factored form to determine whether or not we got out a positive or a negative value for everything in that region. There is another way to determine local extrema. If you remember from Calc 1, we would often use the second derivative to find concavity. Function was concave up. If you tested something in a second derivative's factored form, once using a second order critical point, test regions. If you were concave up or concave down, that told you that at a particular x value, if you were concave down, there must be a local maximum at that value. If you were concave up, there had to be a local minimum at that value. For local extrema in 3D, we're going to use a particular second derivative test. You can look in your books for Theorem 11. But instead of having an x-coordinate that tells us where our local min or max is, our critical point this time will be an ordered pair. That will tell us where the local min or max is occurring. We use something called a discriminant or a Hessian of the function. You're going to want to know that. It finds local extrema and saddle points for us. I'll show you in just a minute what local extrema and saddle points look like. The discriminant can be three things: less than 0, equal to 0, or greater than 0. If the discriminant, which is above f sub xx times f sub yy minus f sub xy quantity squared, is less than 0, then that coordinate is a saddle point. If the discriminant is 0, you know nothing because the test is inconclusive. If the discriminant is greater than 0, then there will be a local extrema. It could either be a local min or a local max. You're going to have to do something else to figure out whether it is a local min or a local max. if f sub xx is greater than 0, positive in other words, then you'll have a local minimum. If f sub xx is less than 0, then your ordered pair will be a local max. Often I'm asked, why not look at f sub yy instead of f sub xx? You can, but you don't have to look at both. Doesn't matter. What are saddle points? Well, look at these two graphs. Both of these have saddle points at the origin of the graph. This one over here is easier to see. You have a saddle point located right there at the origin. This graph shows you local extrema. You have local maxes here and here. This is where they are located at those particular points. And you have a local minimum right here. Your steps for finding local extrema or saddle points are right here. Taking partial derivatives, finding that critical point, that thing right there. By finding the values of x and y's, you're either going to solve, you may solve a system, you may use permutations. I'll explain that when we get to problems like that. And then applying the theorem of the discriminant. So let's look at example 14.7, problems like numbers 1 through 30. You're supposed to find all of the local maxima, minima, and saddle points of the function. So step 1 says to take all your partial derivatives. So take a second, please, and make sure those partial derivatives make sense to you. Step 2. Find the critical points by setting the partial of x to 0 and the partial with respect to y equal to 0. Solve those two equations and that gives you your critical point. So in this case, it's the ordered pair 1, 3. That's my ordered pair AB. Third, apply the discriminant. So you are multiplying f sub double x times f sub double y minus f sub xy squared. So you can see those values, and that's equal to 4, which is greater than 0. So according to my theorem, I do have some kind of local extrema. To figure out what that local extrema is, I go back and look at f sub xx. It's 2. It's positive. So because that's positive, I have a local min. Now, the value of that local min I could find by doing f of 1, 3. But the local min itself, if I'm writing it all out, here's the x coordinate, here's the y coordinate, here's the z coordinate. Doesn't matter to me if you leave your z coordinate like this or if you actually find z. Let's look at another example. Same directions. Here's my function. So here are all of my partials. Please notice that unlike the last problem, this time my partials have variables in them. They are not constants. So I am setting f of x equal to 0 and f of y equal to 0 and solving. Here's what I mean by permutations from step 2. To find these critical points, I'm going to make an ordered pair with 0, 2, and then with 0, -2. Then I'm going to repeat the process with my 3. 3 positive 2 and 3 negative 2. So your discriminant for step 3 uses f sub double x, f sub double y, and f sub xy quantity squared. You are going to plug all 4 of these ordered pairs into your discriminant, right up here. You might want to pause the video for a minute and plug one or two of those in so you can make sure you understand what I'm doing. Notice that I also have a last column for whether that value of the discriminant that I get out is positive or negative. The 2 values that come out that are negative tell me that I have saddle points. So I have a saddle point whose coordinates are 0, 2, and f of x comma y. Can't get a number there. I also have one whose coordinates are 3, negative 2, and f of x comma y again. The 2 values that are greater than 0 give me local extrema. To figure out whether a point is a local min or a local max, I'm going back to my f sub double x, and I am plugging in the 0 because there's nothing to plug in for the negative 2 yet. I get out a value that is negative. 2 times 0 is 0, minus 3 is negative. So that means I have a local max at 0, negative 2, f of xy. I then plug in 3 into the same place, but this time I get out a positive, which is greater than 0. So 3, 2, comma, f of x comma y is a local min. Let's do one more of these. Same directions. Find all your partials. Do you notice that you have variables in your partials, but not just one variable? For example, your partial derivative with respect to x is 2x minus 4y. So this time when I go to find my critical points, I'm going to have to solve a system. I'm taking f of x and setting it equal to 0, and the partial with respect to y and setting that equal to 0. Notice that I have 2 equations in 2 unknowns. So I'm going to solve this system by substitution. I'm going to solve this equation for x. I get x is equal to 2y, and then I am taking that and putting it into this equation everywhere that I have an x. That gives me, when I do that substitution, this equation right here, which is a quadratic equation that I can factor, and I get out 2 solutions. Y is equal to 2 and y is equal to 2/3. Now that I know y, I can plug that back in x is equal to 2y to figure out what x is. When I plug in y is 2, I get out x is 4. When I plug in y is 2/3, I get x is 4/3. So I only have two critical points. X is 4 when y is 2. X is 4/3 when y is 2/3. I do not have any permutations this time because I had a system. It's probably a good idea for you to write down your discriminant a couple times. So here it is again. So f sub double x, f sub double y, f sub xy, quantity squared. Finding my discriminant again, plugging in 4, 2, that ordered pair into my discriminant. I get out an 8. Plugging in a 4/3, 2/3 into that, I get out a -8. What do we say when our discriminant is less than 0? Do you remember? We have a saddle point. I'm waiting for all of you guys to answer together. When the discriminant is greater than 0, we have either a local min or a max. In other words, some kind of local extrema. So I need to go back to f sub double x. That's a constant, not a variable. I don't have to plug anything in. So f sub double x is greater than 0, which tells me I have a local min. If you happen to decide to plug in for, never mind. Now let's discuss absolute extrema, not local. If you recall in Calc 1, to find absolute extrema, we tested two things. We tested local extrema, local max, local min, and we tested the endpoints of our domain, kind of like boundaries. So in other words, I would test this point and that one. In this particular function, based on the domain of 1 to 6 inclusive, the absolute max of the function, the y values in other words, would be an absolute max of 7 and an absolute min of 2. We would find these without a graph by plugging the x values of local extrema and endpoints of the domain into my original function to figure out the largest and the smallest y values. We did not use a first or second derivative test. Now we're going to find absolute extrema, absolute maxes and mins, over a given domain. Here's your function within a region bounded by these three equations. So the first thing I'm going to do is graph these equations. Next, I'm going to find my critical point. So partial with respect to x, partial with respect to y. Set each of those equal to 0. Solve, and my critical point is 1, 3/2. Now I need to figure out whether that is in the bounded region. 1 3/2 would be about right there. And yes, that is in the region. that is bounded by the three equations that I was given. Recall from Calc 1 that to find absolute extrema, I test local extrema as well as the endpoints of the domain. So my bounded region is going to give me some additional points to test to see if they are absolute extrema. So pay attention because this is going to be completely new. My original function, f of xy, was equal to 5 plus 4x minus 2x squared plus 3y minus y squared. I am taking my very first line within my bounded region, y equals x, and I am going to replace the y coordinate with an x. So I am replacing this y and this y with x's. Simplifying that gives me this new equation. Next, I'm taking the partial derivative with respect to x of this function, giving me negative 6x plus 7, set that equal to 0 and solve for x. Since y equals x, if the coordinate for x is 7/6, the coordinate for y is also 7/6. Double check that that is on your boundary. Yes, it is. It would be approximately right there. Oh, I missed, but you get the idea. Now repeat that process with y equals negative x. In my original function, I am replacing every y with a negative x, giving me this function. Simplify it. Take the partial of this function with respect to x, set it equal to 0, solve for x. If x equals 1/6, then y must equal negative 1/6. But that would not be on my boundary because that would be like down there. Repeat the process a third time with y equals 2. So in my original function, everywhere I have a y, I am putting a 2. I then simplify that function, getting negative 2x squared plus 4x plus 7. I am taking the partial derivative with respect to x of that function, setting it equal to 0, solving for x, which gives me 1. So when y is 2, x is 1. Double check that that point is on your boundary. Would be about there. To find the absolute extrema, I need to check the critical point in my function, the values that I found from my boundaries in the function, as well as the vertices or corners of the polygon formed by those three boundary equations that I was given. Remember, I was given y equals 2, y equals x, and y equals negative x. So here's the critical point that I found. These are the two values that I found from the boundaries. And these 3 points right here, I found from my vertices here, here, and here. I am plugging all 6 of those points into my original function. And when I do that, I get out these values. So my absolute min is -9. It's the smallest of all 6 of those outputs. The absolute min occurs at -2, 2. My absolute max is the largest of those 6 outputs, and it is 37/4 or 9.25, and it occurs at the location 1, 3/2. This is one that I'd normally let you guys do alone, or with a table partner. So I'm going to let you do that now, but I'm going to point out just a couple of things to you. Please note that this should be on your notes. It's another line for your region boundaries. I've graphed the region. I'm finding critical points. I'm checking boundaries. And then I am plugging all of those, the critical point, the one critical point, the 4 values I find from the boundaries, as well as the 4 vertices into my original function.